Hello, I thought I would do a couple of examples with trying to solve second order differential equations where we have the unit step function involved. We're going to do two examples, and the first one, the forcing function, the function on the right side of the equations, we'll call g of t in a minute. This problem is worked out. It's the file step.pdf, and this is on Canvas. So I would advise you to download it and go through it with me, and that way you won't have to write anything. The second problem was selected because it has a mixture of unit step functions and a normal function, a function that's not stepped. So this function would be in effect all the time, and then this comes into play after t equals 2. Now, what we're going to need, we're going to need these results from the textbook. So the Laplace transform of the unit step function is an e to the minus as over s. Now, if you let the Laplace transform of f of t be f of s, you look this up in the table, whatever f of t is, you would just look it up into the table, and that's going to be your function f of s, capital F of s. Now, the Laplace transform of a stepped function when the arguments both agree is simply e to the minus as, that comes from the step function, times then the Laplace transform of f of t. Now this is wonderfully simple when you can get this. When the variable in the problem is t minus a everywhere, and we step it with the unit step function at t minus a, then the Laplace transform is an e to the minus as, that comes from this part, times then the Laplace transform of just f of t, not f of t minus a. Now, that's great when it happens, but it often doesn't happen. Typically, the arguments of the function and the unit step function, they do not agree. Well, what do we do then? Well, we have this. This is the situation. Here's the step function, t minus a. And the function g does not have that argument. The argument of g is not t minus a. What we do then, we get an e to the minus as from the unit step function, and then everywhere in the function g that you have a t, you replace that with t plus a, and then take the Laplace transform of that. Okay, now you have the advantage. Anytime you want, you can simply pause the video, catch up, rewind it, etc. But here's the two examples we're going to look at. Here's the information we're going to need from the textbook, and let's go through the problems. All right, example 1. Here it is written in its form. Now, what I did, I went ahead and graphed this so you can get some kind of representation. If you're given a problem and only given the graph, the first thing you want to do is go from the graph to this piecewise defined function. But what we need to do first is write this function and write this graph in terms of the unit step function. Now, the way I teach this, the way I do this, It's very elementary. The book makes some sort of comments. You can just look at this and get the answer. No. So let's go through this. The function g of t now it is 0. It's turned on at u of t, and it's turned off at t minus 10. So always remember, you have to have it on and off. Now what happens? That puts us right here. Then at 10, we have an amplitude, a jump of 1, so it's going to be plus 1. And it's turned on at u of t minus 10. And then we shut it off at 20. So again, it comes on, the amplitude is 1. It's turned on at 10, turned off at 20. Now right here at this step, I'm there. Then what happens? Well, it's 0. It's turned on at 20 and never turned off. Now, if you proceed that way from left to right, put your jumps in, turn it on, turn off, you won't ever get into trouble. Now, we want to simplify this. You always wish to simplify this. Always. This part gives us a 0. This part gives us a 0. So this is just u of t minus 10, and then u of t minus 20. So that function g of t in piecewise defined form and g of t in terms of a graph can be written just this way. So then our differential equation becomes, we have the second derivative plus 2 times the first derivative is equal to u of t minus 10 minus u of t minus 20. And the conditions are that y sub 0 is equal to y prime of 0 is equal to 0. Okay? Now make sure you got that. You've got to be able to get that. The problems are generally two kinds. Sometimes, like the next problem we do, this is going to be given in this form, but sometimes you have to do this. And your fifth quiz, I'm going to give you something like this, and your job is going to be to write it in terms of unit step functions and simplify, and then take the Laplace transform. So that's what quiz 5 will be. Okay, now we take Laplace transforms of both sides. This is going to give us an s squared y of s minus an s y sub 0, always the same thing, y prime of 0. That's your second derivative. And then 2 times the first derivative, the Laplace transform of the first derivative is s times y of s minus y sub 0. And that's going to be equal to what now? Well, we have to take the transform of this. And using the theorem definition that I brought up earlier, the Laplace transform of this is going to be an e to the minus 10s over s minus then the Laplace transform of this term is going to be an e to the minus 20s over s. Now, putting in what we're given that this is 0, this is 0, this is 0. That's then going to give us an s squared plus 2s y of s. That's all we have on the left side. And then this is going to equal an e to the minus 10s minus e to the minus 20s all over S. Now that's going to give us y of S is equal to e to the minus 10s minus e to the minus 20s. And then downstairs I'm going to have an s. I'm going to have an s from this side. So that gives me s squared times s plus 2. Okay. I'll pause for you to catch up. Catch you on the next page. All right, here we are. This is the result from our previous work. Now, of course, it's time to find an inverse transform. But we have these e to the minus 10s and e to the minus 20s. What we're going to do is just ignore them. We're just going to ignore them. If you wish, you can think of it this way. Some people like to do this. It does no harm. We can think of this as e to the minus 10s. And then downstairs we have s squared times s plus 2 minus then e to the minus 20s over s squared times s plus 2 again. Now the e to the minus 10s, anytime in the s domain, anytime after you've taken Laplace transforms, you have the exponential. That means that part of the problem has been stepped. It's going to only apply after 10, and this part's only going to apply after 20. Well, what I want to do is ignore all of them, and let's do a partial fraction decomposition on just this. And that's what you generally do. You just ignore the stepped parts. These are just indicators. These are screaming at me, hey, this is being stepped. Now, let's do a partial fraction decomposition. We all know by now how this is going to play out. And we get our common denominator like we always do. This would be an as times s plus 2 plus then a b times ds plus 2 and then a c times s squared. Just the usual thing. We want to make each denominator look like the one on the left. And you simply just multiply top and bottom by what's missing. And then we want to equate numerators. Now we go to work. We've got 3 unknowns. So let's simply let s equal, how about 0? If I let s equal 0, I have 1 equals. Well, that term's going to be 0. That term's going to be 0. If we let s equal 0, we just simply get 2b. So b, of course, is going to be 1/2. Okay, now let s equal minus 2. I've got 1 equals, now if s is minus 2, these two terms are 0. Now minus 2 squared is 4, so that's going to be a 4c. And that then means that c is 1/4. All right? That should be routine. You should be able to roll through that pretty quick. Now just pick anything else for s. Anything but 0 or minus 2. Let's just use a 1. Now, I'm going to have 1 equals. Okay, we put a 1 in here, we get 3a. And remember, we know values for b and c. So if I put a 1 in here, I get a 3 times b. So that's going to be a 3/2. And then 1 squared is 1, so we just pick up a 1/4. And this is 1 equals 3a. Now if we add together 3 over 2 plus 1 over 4, That's going to be plus 7 over 4. So 3a is equal to 1 minus 7 over 4. So we get 3a is equal to minus 3 over 4. So a is equal to minus 1/4. Okay, check that out. Make sure you've got that. Now, what would the answer be if there were no step functions involved? If we just looked at this, now I'm going to write this in red. If there were no step functions involved, then y, and I'm going to call it y temp, the temporary answer would be just negative 1/4, right? The inverse transform of 1 over s is just 1. And then plus a 1/2 t plus a 1/4 e to the minus 2t, right? Just inverse Laplace transforms. But see, now this answer is going to be stepped at 10 and at 20. Does that make sense? So what's the final answer going to be? Well, it's going to be this. My pen will write. So what I'm going to have is this part stepped at t minus 10. Now, what that means is this theorem right here must be obeyed. It must be obeyed. See, this is what we did the partial fraction decomposition on. It's going to be stepped, and that means from the exponential part I pick up a u of t minus a, and now I take the answer that we got in red, and everywhere there's a t, put t minus a. In this first part, it'll be t minus 10. All right, that means then I'm going to have a negative 1/4 plus 1/2 t minus 10 plus a 1/4 e to the negative 2 times t minus 10. And that's all stepped u of t minus 10. Now up here we have a minus. So minus, now it's going to be the same thing, except this time I'm going to replace the t with t minus 20. And that's it. That's the solution to that first example. Now, if you look at the handout, I went ahead and simplified all this stuff. But if you are ever in the situation that you want to plot the solution and see what it looks like, that Desmos graphing utility on the web, that web page, you can type this in just like this, and there's no need to simplify it. Okay, let's look at it. The second example. I'll have it ready in just a second. Okay, here's the second example. Now, I chose this one for a specific reason, because on the right side, we have a normal forcing function. And then in addition to that, we have a stepped part. So what's going on? This side, this left side is being driven by this always. However, when t equals 2, when t equals 2, this comes into play. And you see that when t equals 2, this is turned on, the t subtract out, and you have minus a minus 4. So if you wanted to graph this, the graph would be y equals t, a 45-degree line, and then at then at t equals 2, it's just y equals 4. Okay? But this is what we're given. We're given a mixture, and I thought this was a pretty cool problem. Here are the initial conditions. So, we start by taking the transform of both sides. And by now, you should know this stuff by heart. Okay? There's the transform of the second derivative. Now, it's just going to be the function y of s. Okay. However, what's going to go on here? Well, the Laplace transform of t is straightforward. It's 1 over s squared, straight from the table. But now, what's going to go on here? So let's look at this. What is going to be the Laplace transform? Let's put the minus out front. Let's keep track of the minus. So I've got minus the Laplace transform of t minus 4, u of t minus 2. It would be so nice if these arguments agreed, but they don't. This is t minus 2, that's t minus 4. So here's what has to be done. I'm going to get a minus, and I'm going to get a minus e to the minus 2s. That's from the step function part. And then I need to take the Laplace transform, and what I need to do, I need to replace that t with t plus 2. So I've got t plus 2 minus 4. So I need to take the Laplace transform of t minus 2. So I have to obey that theorem earlier. You can't get around that theorem. That theorem has to hold in every problem. So when the arguments disagree, we simply replace t with t plus 2. So I've got t plus 2 minus 4. So if we go ahead and do that, that's going to be a negative e to the minus 2s. The Laplace transform of t is 1 over s squared. Laplace transform of 2 is 2 over s. So this is going to give me a negative e to the minus 2s. If we get a common denominator, we have 1 minus 2s over s squared. And then what I'm going to do is eat that negative sign. I don't like those. So I get an e to the minus 2s times 2s minus 1 all over s squared. So that's what's going to be the Laplace transform of the portion of the forcing function that's stepped. So right up here, I'm going to have a plus e to the minus 2s times 2s minus 1 over s squared. All right, now before we go any further, make sure you got that. Now let's use our initial conditions. This is going to be 0, and this will be a 1. So let's see what that gives. That's going to be an s squared plus 1 y of s. Now, I've got a 1 here that I need to take over to this side. See, that negative 1, there's a negative 1 on the left, and I need to move it over here. So I'll add 1. Okay, now, one more little task before we rock and roll here. So get a common denominator here. This is s squared plus 1 over s squared. And then I've got a 2s minus 1 over s squared e to the minus 2s. Okay? Now what I need to do is divide everything through by s squared plus 1. And we're going to have a little happy accident. Watch this. Now, do you see the happy little accident? Look what happens here. It turns out that those just cancel. We did get fortunate. We got very lucky. So this ends up just being 1 over s squared, which means we're through with the portion of the problem that's not stepped. Because in a minute, when we take the inverse transforms, we don't have to do anything. We know that this is just a t. Now, if that had not canceled, then we would have to go and do a partial fraction decomposition on this piece that's not stepped, then do a partial fraction decomposition on this part, and it is stepped. But as it is, we get lucky. That's fine like it is. Okay, now we need to look at the partial fraction decomposition of the stepped part of this problem. Okay, let me get that set up. Okay, so here we are. Here's the portion of the problem that's stepped. And again, we just ignore the e to the minus 2s. All that is an indicator. It's a beacon that's telling us that that portion of the problem is stepped. So now we look at the partial fraction decomposition. Here's what we've got. Now notice there's an s squared plus 1 in here. So that means I could have a cosine and I could have a sine. For it to be a sine, there needs to be a 1 here. And this m simply tells me how many sines I'm going to have. In a similar fashion, to match what's in the table, for cosine we need this, and this number simply tells me how many cosines I'm going to have once I take the inverse transform. So as usual, we do our normal thing here for the decomposition. Now we're going to get an a times s squared plus 1, a b times s squared plus 1, an ms squared, and then we'll have ns times that denominator s squared, so this is ns cubed. We have 4 variables to find, a, b, m, and s. Okay, so let's let s equal 0. That's as good a place to start as any. If we let s equal 0, we have minus 1. Now this term, and this term, and this term, all 0. If I come over here and let s equal 0, we just get b. Very nice. We know what b is now. For the rest of the problem, we know that b is minus 1. Okay. Now, let's let s equal 1. If I let s equal 1, I've got 2 minus 1 is 1. Now, if s is 1, this is a 2a. Remember now, b is minus 1. So this turns out to be a 2. A 2 times minus 1, so it's minus 2. S is 1, we just get plus m, and then, of course, plus n. So we have 2a plus m plus n equals 3. Okay? That's one equation. We're going to need 2 more. We want to have 3 variables and 3 equations. We're going to throw that in the calculator just like we did in class and let it give us the answer. Okay, let's try s equals anything minus 1. So that'll be negative 2 minus 1, so that's minus 3. Now s is minus 1. Minus 1 squared is 1, so that's a 2. That's a minus 1, so this is minus 2a. Negative 1 squared is 1, so that's 1 and 1 is 2, but b is minus 1, so this is minus 2 again. Negative 1 squared is 1, so that's plus m, but negative 1 cubed is minus 1, so it's minus n. So this gives us minus 2a plus m minus n equals minus 1. Okay, now notice, if you're paying attention, we could simply add these two together and find that m is 1. But I'm not going to do that. I'm going to wait and plug it in to the calculator and review how to do that sort of thing. Okay, so let's let s equal 2. Well, that gives me 4 minus 1 is 3. Now s is 2, so that's going to be 4 plus 1 is 5. Times 2 is 10, so I get a 10a. That's going to be 4 plus 1 is 5, but remember b is minus 1, so it's minus 5. 2 squared is 4, so we have a 4m. And then 2 cubed is 8. 8n. Now add 5 to both sides, and we end up with 10a plus 4m plus 8n is equal to 8. Now if we divide by 2, we get 5a plus 2m plus 4n is equal to 4. Okay. So, I'm not sure how this is going to show up in the calculator. But I want to take that information, and you can just pause here. Well, that shows up actually pretty good. So I'm going to create matrix A. It's going to be 3 equations, and there's going to be 4 columns, 1, 2, 3, 4. Okay? And we just type the information in. Okay? Now once you get it typed in, we quit. Now we go back into matrix mode, and we go over to math. Use the down arrow, use the up arrow, doesn't matter. But what we want is B, which is RREF, double REF. Now we have to tell the calculator the matrix we're applying this to. So we go back into matrix one more time. We had set this up for matrix A, so I just hit enter. And see, that tells me what my answers are. Now remember, the way I've got this set up, it's column, the first column is column A, middle column is M, last column is N. So this tells me then that A is equal to 2, M is equal to 1, and N is equal to minus 2. Okay, now make sure you can get that. Okay, then, what do we have? Well, we know that A is 2, M is 1, and the N is minus 2. So again in red, if I were to take the transform of just what's at the top, then I would end up with a 2 minus t plus sine of t, and then minus 2 cosine of t, right? Those are the terms I would get. And just like the last problem, we're going to take this and step it. We have an e to the minus 10s. That's going to be a step, u of t minus 10, minus then the same expression, stepped, u t minus 20. Okay? So let me get that stepped up. Okay, from the previous page, if we took the inverse transform of what we got in the partial fraction decomposition, we would get this in red. But now see, remember, remember we had an e to the minus 10s. That means it's going to be stepped. The e to the minus 10s is going to generate this in the solution. So we need to take this expression, and everywhere we have a t, put t minus 10. Then remember we had minus an e to the minus 20s. Well, that generates this. So we then need to take this expression we got from the decomposition, and everywhere you have a 10, you're going to put t minus 20. Everywhere you have a t, you're going to put t minus 20 and then step it. So that is what the general solution looks like. Now understand that this can be simplified, but it's just not worth the effort. Most graphing utilities can graph this just as easily as the simplified part. Okay, I hope that helped a little bit, and along with what we're going to do in class on Thursday, you should be in good shape for Laplace transforms. Hope it helps. Thanks.